We're now in the second stage of glucose metabolism. We've entered the mitochondria, and we are now going to cover the citric acid cycle. For every glucose, you can see that we only make, again, 2 ATP directly through the citric acid cycle. But what we're going to focus on is the NADH and FADH2 that we're going to then bring to the electron transport chain. So next time, we're going to talk about the electron transport chain and how we make ATP from that, because you can see that we're making a great deal more with oxidative phosphorylation. So we're going to see how we're going to take that pyruvate and make it into the citric acid cycle by first making it into acetyl-CoA. We saw that a little bit in the last lecture, but we're going to see exactly what is happening there. So again, the first thing we're going to cover is going from pyruvate to acetyl-CoA. We're then going to, again, just like we did with glycolysis, take a look at the individual reactions. We're going to talk about how we, because it's a cycle, we put in 2 carbons from acetyl-CoA, how we, when do they go out? Are the 2 carbons that we put in the same that to go out as carbon dioxide? So we're going to answer that question. Of course, we're going to talk about regulation. How do we turn on and off this cycle? Then we're going to look at the only anabolic pathway we're covering this semester, the only building up cycle, and that's the glyoxylate cycle. It parallels the citric acid cycle in many ways, so we're going to see how it's similar and different. And then we're going to see how we can use the intermediates of the citric acid cycle for other things. Either we can feed in or we can take things out. That's why it's called the central metabolic pathway. So again, we're going to cover the citric acid cycle. We still have yet to cover electron transport and oxidative phosphorylation, so that will be next. But those are the parts of aerobic metabolism. So without oxygen, we're not going to have the citric acid cycle take place. So again, I've been saying these words, catabolic and anabolic pathways. So catabolic, again, is breakdown, but I want you to think of it as oxidative. We're taking those carbons and making carbon dioxide. Anabolic is a reductive method. So we're going to be taking carbons and putting hydrogens on them. We're building up. So catabolic, you're oxidating, you're taking away hydrogens, putting in oxygen. Anabolic, you're taking away oxygen, putting in hydrogens. And so the citric acid cycle can be thought as amphibolic. It plays a role in both catabolic and anabolic pathways. I said it was the central metabolic pathway because it's related to so many other pathways. At the end of today's lecture, we're going to spend a little bit more time on that. Oops. So again, I said that the metabolism of glucose is in 3 parts. Glycolysis, which every cell has, and that takes place in the cytosol. It's anaerobic. So we covered that in the last lecture. And then the acetyl-CoA is the entry molecule for the citric acid cycle. This happens in the mitochondria. But you can see that these electrons, who's carrying these electrons from either glycolysis or the citric acid cycle to electron transport chain? What molecules? Yeah, our reduced coenzymes, our NADH. That's right. Our reduced electron carriers. I like to think of them as bucket brigades, that they're just holding the water is the electrons, and they're the people holding the waters. Without oxygen, we do not have the citric acid cycle and electron transport. Excuse me. So the citric acid cycle takes place in the mitochondria, and it actually takes place in the matrix. So we're going to see how that happens. I said at the beginning of the semester I wanted to have more of them. I don't. I didn't run it more. Life just takes hold and doesn't let me work out as much as I want to. All right, so this is really tiny, but maybe you guys can see that it's a cycle. You come back to the starting material. So this is different than the glycolysis that we saw in last lecture. There's 2 different parts of it, really. This is not part of the citric acid cycle. This is the pre-citric acid cycle step. So we're going to take a look at that first. And then here we have the cycle. Where I like to look at, we're adding 2 carbons through acetyl-CoA, And the first half of them, we're going to get rid of them. See these little green things? We're going to get rid of those carbon dioxides. And then the second half, coming back up, the other side of the clock, you might think, we're coming back up to the starting material. So in a nutshell, we're taking 3 carbons from pyruvate, say 1, 2, 3, and we're breaking it down to 2 carbons and acetyl-CoA. So see, this is the acetyl-CoA. Remember when we introduced that coenzyme, I said all I want you to remember from that structure is the sulfur, because the sulfur is where it's going to join to the group that it's carrying. So you can see the sulfur is connected to the carbonyl of the acetyl group. So we go from 3 carbons to 2 carbons. We're losing a carbon dioxide. We lose this acid group. That's an oxidative decarboxylation. Again, I'm introducing this now. We're going to go over it again. This is an oxidative decarboxylation. We're losing a decarboxylation means we're losing a carbon dioxide. And so we're losing a carbon. When you oxidize, we have to reduce. We get a money molecule here, NADH. Right? Remember, it's not a direct money molecule. We're going to have to turn it in through the electron transport chain, but we get an NADH. So we get some benefit from this pre-citric acid cycle. We get some energy through NADH, and we lose a carbon dioxide. Do you think it's regulated? We're losing a carbon dioxide. Every time you lose something valuable, and carbons are valuable, think that resources are limited. We don't, in evolution, things weren't plenty like they are now. So if you're going to lose a carbon through carbon dioxide, you better make sure that you need to lose that carbon. So instead of using pyruvate to build up, we're going to use it for energy, and so you better be sure that you need to do that. So this is definitely under control, right? You see that there's 2 other steps where we have the loss of carbon dioxide. Do you think those are under control as well? Yeah. Remember in glycolysis, the points that we inputted energy as ATP, those were under control. Here, when we're losing something valuable, those are under control as well. All right, so what we have is 2 carbons going in. We're going to condense it with a 4-carbon molecule called oxaloacetate. So you put the 2 carbons from acetyl-CoA together with 4 carbons of oxaloacetate. So here we have 6 carbons. 3 of them are acids, right? And then 1 is what kind of alcohol is this? Remember, is it a primary, secondary, or tertiary? It's a tertiary alcohol. Remember that catabolic metabolism is an oxidative process. Can we oxidize a tertiary alcohol? No. So look what's going to happen next. We're going to summarize a tertiary alcohol to a secondary alcohol. So then later we can oxidize it. Think how smart it is. Nature knows you can't oxidize a tertiary alcohol. So it's going to do it for you. It's going to move it so it can do that. So smart. So also look at citrate. Acid, acid, acid group, and then alcohol. Now we move that alcohol so that in this next step, what we're going to do is decarboxylate. We're going to lose this carbon dioxide, or this acid group as carbon dioxide, and we're going to oxidize this now secondary alcohol to a carbonyl. So here you're oxidizing and losing carbon dioxide, so we're going to reduce. We're going to get some money, NADH. The next step, we're going to lose another carbon dioxide. We're going to lose here, but we're going to condense with a coenzyme A. All right, so we put that on here. That is also an oxidation. So what we're doing is we're reducing an NADH. Then we break this. This is a high energy bond. We break that, and because we're breaking a high energy bond, we get some money. GTP is a molecule just like ATP. It can directly give it to ATP. So that's, you can think of it that we get an ATP out of it. Remember though, we get 1 ATP from 1 pyruvate, but how many pyruvates do we get from glucose? 2, right? So you can double that. All right, depending on the way the question is phrased. So when we cleave this high energy bond, this is going to go to an acid. Succinate is a symmetrical molecule. Now, what I want you to do is take a look at this molecule and compare it to this molecule. All right? Acid, acid, CH2, CH2. Acid, acid, CH2, oh, carbonyl. So we have to get an oxygen there. Those of you that have taken 2 semesters of organic chemistry will know that what you do is you put a double bond in, you hydrate and oxidize. That's what you do in the lab. If you did a synthesis scheme where you needed to put an oxygen on a carbon, then that's what you would do. Now when you put a double bond in, that is losing 2 hydrogens. That's an oxidation. A different type of oxidation, but it's still an oxidation. It's tougher to do, so we need a stronger oxidizing agent. FAD is going to do that job for us. So when you put a double bond in, a lot of times you're going to see FAD as the oxidizing agent. So we get another money molecule, FADH2, from this. So here we put the double bond in. We're going to hydrate it so that we get an OH, and then we're going to oxidize it. And we get some more money out of there, another NADH. So overall, we're putting our pyruvate into the pre-citric acid cycle, get some money out of that, NADH and the carbon dioxide. The entry molecule from the citric acid cycle is acetyl-CoA. We get out 2 carbon dioxides. We're going to learn that they're not the same carbons that we get in, we put in here. We're going to get how many NADHs? 1, 2, 3 NADHs, an FADH2, and a GTP or ATP. You can say either or, I'd be fine with that. All right, so there's a lot going on here, but it's, it makes sense, all right? For me, if you think about what is going on with this, you put 2 carbons in, you're going to get 2 carbons out. It's a cycle. You're going to get back to the starting material. How would you do that? So it absolutely makes sense. So now what I'm going to do is focus in on this pre-citric acid cycle. How are we going from pyruvate to acetyl-CoA? And the enzyme that we use is pyruvate dehydrogenase complex. Again, this is for coenzyme A. It's made of, it functions to carry groups. All right, it carries most of the time acetyl groups. And the only part that I really want you to remember from this structure is this sulfur, right? This sulfur, that this is where it's going to attach to it. You know, it's nice to know it's got a sugar ring, some phosphates, an acid, you know, so it's really, but it's really the sulfur. And remember, sulfur has those lone pairs. It's going to attack a carbonyl. Yes? The group that it's carrying. So what's going to attach to the sulfur is the group that it's carrying. So to go from pyruvate to have our acetyl group be on this sulfur takes a whole series of reactions. So we're going to take a look at it. And what I want you to focus on when we look at it is what's carrying what, what's going on, what is the purpose of each component of this glob. Really, it's that enzyme for the pre-citric acid cycle, going from pyruvate to acetyl-CoA, happens in a big glob. And this big glob has 5 enzymes in it. I just want you to remember it as the pyruvate dehydrogenase complex. You don't need to remember all the names of the enzymes that take part of it.
Say what it's supposed to be one more time. The pyruvate
Dehydrogenase complex. Right here, pyruvate dehydrogenase complex. No, it's quite all right. There's a lot going on in there. Now, this slide is more for you to read while you're looking at the next slide. So I'm going to just briefly go over it, but I'm going to focus on the next slide because that's where the action's happening. So there's the first step that happens in this pyruvate dehydrogenase complex is that we're going to lose the carbon dioxide. We're going to lose that acid, all right? And that TPP group that we got introduced at the end of last lecture is going to hold on to that. And then we're going to transfer the group to a lipoic acid. And then we're going to transfer from the lipoic acid to coenzyme A. So there's a lot of words here. What I want to do is look at what's happening because it makes a lot more sense. This is from the textbook. Here, This is TPP. This is the rest of the structure. If you look back at last lecture, you can look at the whole structure. But really the only important part is that it's going to connect. So TPP, diamine pyrophosphate, what it's going to do is it's going to attack this carbon of a carbonyl right here in the middle of our pyruvate. This is our product from glycolysis. Pyruvate's going to come in. TPP is going to attack this, and it's going to have the carbon dioxide leave. So the acid group is going to leave. So what we have is this hydroxyethyl, right? This is hydroxy, 2 carbons ethyl. So hydroxyethyl TPP. The next step is that we're going to oxidize this. Lipoic acid is going to do that job. So when we oxidize, something has to be reduced, right? Anytime you have an oxidation, something has to be reduced. So when we oxidize the alcohol, the secondary alcohol, to a carbonyl, something has to be reduced. So this is a weird view. This is a protein, and then this is sort of different moments in time. This lipoic acid, and this lipoic acid. This is like 3 different ones. When you have a sulfur-sulfur bond, that's an oxidized form of sulfur. When you have a sulfur-hydrogen bond, that's a reduced form of sulfur. So right here, in this moment of time, we have the oxidized form of the sulfur in this lipoic acid. This sulfur-sulfur bond gets reduced. You now have a sulfur-hydrogen bond. This sulfur is available to attach to this carbon. So the TPP gives up this group, gives it to the sulfur, and this becomes oxidized while the lipoic acid gets reduced. So what I want you to remember so far from this is that we lose a carbon dioxide, we go on to TPP as an alcohol. So pyruvate is losing a carbon dioxide, it's going on to TPP as an alcohol. Then it goes on to lipoic acid as a carbonyl, as a thioester, really, because the lipoic acid is going to get reduced and our group is going to be oxidized. Do you want me to say all that again?
Yes.
We have 3-carbon pyruvate. In the first step, we're losing carbon dioxide, and the group is going on to TPP as an alcohol. The 2-carbon group, the 2-carbon alcohol. In the next step, we're moving this 2-carbon alcohol group to lipoic acid. But at the same time, an oxidation happens. We're going to oxidize this alcohol to a carbonyl. We decarboxylate, but as it's not a really reduction, it's decarboxylation. But it's part of the, hold on one second, as part of that decarboxylation, this becomes an alcohol because the DPP group is going there. This is what we're losing. This one is going to become an alcohol. Yep. Yeah. It's part of the decarboxylation process.
Can you just repeat that lipoic acid part?
Oh, sure. So the alcohol is going on to the lipoic acid. The alcohol gets oxidized while the lipoic acid gets reduced. It's opening this lipoic acid ring. That's the reduction process. So if I showed you a sulfur-sulfur bond and a sulfur-hydrogen bond, you would say that the sulfur-hydrogen bond would be the reduced form. The sulfur-sulfur bond would be the oxidized form. Now, the coenzyme A, sulfur, is a better nucleophile than this sulfur here. So what's going to happen is that the acetyl, now see this blue thing here? That's called an acetyl group. When you have a carbonyl and a CH3 next to it, that is what we call an acetyl group. So from now on, when I say acetyl, you're going to think carbonyl CH3. So the acetyl group is transferred from the lipoic acid sulfur to the coenzyme A. And what makes it better? It's the rest of the molecule, right? When we looked at the molecule of coenzyme A, that stuff that sulfur was bound to on the coenzyme A changed the nature of that sulfur compared to the nature of this sulfur. Right? I'm not going to get too far into the organic chemistry of it, but I just want you to realize that a sulfur is not just a sulfur. A sulfur is a sulfur depending on its environment. So if you can think of it, the sulfur on the coenzyme A has a more supportive environment to hold this acetyl group than the sulfur on the lipoic acid. It's like having a good background, you can achieve more, right? So this is a better background. That's the way I think of it. All right, so we have this lipoic acid that's in the reduced form. We need to get it back because that's part of an enzyme. You get back to the original form. So we need to oxidize it. You oxidize it, something needs to be reduced. Here we get some money. Don't pay attention to FAD, just the NADH. All right. So TPP, lipoic acid, coenzyme A. I want you to remember that order. And then the reason why we get that NADH is that lipoic acid has to be reoxidized. Another less detailed look at it, more holistic look at it. 3 carbons, pyruvate, 2 carbons, acetyl, connected to the coenzyme A. So this is what the pyruvate dehydrogenase complex has. You need the TPP, lipoic acid, and the coenzyme A for it to occur. Think 1, 2, 3, and then you get out your NADH and you lose that carbon dioxide. So this is a more holistic way to look at it. Okay, so now we're ready to enter the citric acid cycle. This is oxaloacetate. It's going to condense. Condense means put together. Condense with our acetyl-CoA. That coenzyme A is going to leave, and we're left with, all right, 1, 2, 3, 4 carbons in our oxaloacetate, 1, 2 in our acetyl group. We have 1, 2, 3, 4, 5, 6. All right? So we have 6 carbons. Again, in citrate, we have a tertiary alcohol. Next step, we're going to move it down to be a secondary alcohol, an isocitrate. If you want to complete this, we have an arrow going in at NAD+. NADH needs to come out. Right? So we're getting some money off of this because what we're doing is we're decarboxylating. So you can circle this carbon dioxide, this acid. That's the one that's leaving as that carbon dioxide. And we're oxidizing this to this one. Again, this is the second time we're taking a whole look at it. We're going to take a more detailed look at it again. So we're losing this as carbon dioxide. This becomes, so this is alpha-ketoglutarate. We're then going to lose this bottom acid. And as another carbon dioxide, we're going to get an NADH out of it. And we're going to create a thioester bond with the coenzyme A. Thioester bonds are higher energy. What was your question, Cesar?
So the first one, we lose the top carbon.
No, we don't lose the top carbon. In this first decarboxylation, we're losing this one. Yeah, because you can see we're not losing that one, we're losing this one. So circle this one. That's when we're losing. This one, we're losing this guy. Okay? When we look at the mechanism for the reaction, it's actually these two that are these 2 carbons. So we're not losing those, right? No, not the first cycle. Later on we do, second and third cycle, but we're going to go over that. So now we have a high energy thioester bond. We're going to use that energy to phosphorylate a GTP, which is just like ATP. So you can write ATP as well. So this is succinyl-CoA. This is succinate. Symmetrical molecule, right? So we have to go from here. So if in your mind, you could, if you have an organic chemistry background, you can go from succinate to oxaloacetate. If you know about organic synthesis, what you would do in the lab is what nature does in the citric acid cycle. So you can predict what's going to happen. First, we're going to put a double bond in. Right? That FAD comes out as FADH2. You can complete that arrow if you'd like. Then we hydrate it to make malate. And then we oxidize it. And we get another NADH. So this is fumarate and malate. And then this is our oxaloacetate. So if you notice, as I was going through the reactions, I was telling you why these reactions occur, what is happening with them. And that's what I need you to know from each step. And then we can go over again. If we introduce another acetyl-CoA, we can have that all go in. Where are the NADHs and FADH going, each two going? Electron transport chain. So that's where they're going. Carbon dioxide, we breathe out.